My name is Peter Tanner. I'm working here at the Torocha Institute in the field of risk analysis and structural reliability. And apart from that, I'm also working in a design in an engineering office where we do structural design and also assessment of existing structures. If I'm able to transmit to you the reasons of this title, then it will be good. Otherwise, I will have failed, of course, in 45 minutes. So in structural engineering, we always have to deal with risk and reliability issues. We do not want to produce this kind of situations, of course. And we have to answer questions like how reliable is reliable enough? How much is society willing to pay to reduce the current level of risk, etc. Traditionally, structural engineering always has been a self-regulating field in the sense that codes and standards are produced by the engineering community. And by definition, structures designed and built to code rules are considered safe and fit for use, as these two, hopefully, from our office. Now, these codes treat the safety issues implicitly, so that risk acceptance mainly is based on past experience. And the requirements, in fact, may be insufficient, maybe they are adequate, or maybe they are too high, so that we waste available resources to reduce risks. So this picture actually is from a previous avian flu crisis 10 years ago, where everybody said that there was an overreaction, and maybe nowadays the requirements would be different. This also shows that the requirements may change over time. If we now switch to existing structures, the need to assess the reliability of an existing structure may arise from different causes, but all of them can usually be traced back to doubts about reliability, as here, where we had to add a new roof to an existing grandstand, these typical frame structures, thus completely changing the internal forces and moments, or in this case, where we had to widen the bridge deck, thus increasing the traffic loads. And we have to decide whether the reliability of these existing structures are sufficient for the future use conditions. So the fundamental problem is to find an answer to the question, is the structure reliable enough? In fact, there are only two possible answers, yes or no. But it is not as simple as that, because inappropriate requirements and wrong decisions may imply significant consequences, as well if we do nothing where we probably should do something, or if we overreact and thus waste public resources. So this is the context. Let's now have a quick look at what we do as engineers. We take decisions under uncertainty. Then we will have a look at the main differences between assessment of existing structures and design of new structures. We will see how this topic is tackled in the Eurocodes. And we will also have a short look at needs for further development. Many engineering problems can be described by comparing two quantities, the effects of an action on a system, like here, for example, this block, and the corresponding capacity of the system, the resistance in this case of this wire. The reliability of the system is expressed in terms of basic variables, R and E in this case, by the limit state function. The simplest limit state function is the one that compares R and E, and it is expected, of course, that R is bigger than E. Now, the problem is that the variables are associated with uncertainties. There are different types of uncertainties. First of all, the natural variability. Then statistical uncertainties due to limited data. We usually only have a few data available, particularly if we are talking about existing structures. And there is, of course, also lack of knowledge, for example, about the future evolution of certain parameters, traffic loads, for example, wind velocities also, material strength, etc. And there is also lack of knowledge in models, because every model, even if it is a sophisticated 3D nonlinear finite element model, it is still a model. The outcome of our calculation is uncertain. And then there is also human error, but we will not talk about that because this is supposed to be avoided by quality assurance procedures, etc. There are different possibilities to represent the uncertainties. Normally it is sufficient to represent the variables by their distribution function with a certain mean value and a certain scatter. Now, in design and assessment, structural analysis is based on established engineering theory and practice. Here we have two models for structural analysis. One is for an existing structure and the other one is for a new structure. And I could ask you who is who. I don't know whether you would be able to know which one is the new structure and which one is the existing one. On the other hand, also the general principles of structural reliability are the same for design and assessment. So we may ask ourselves, why should there be then a difference between assessment of existing structures and design of new structures if everything is the same? Also in existing structures and in new structure, we can verify structural reliability in terms of probabilities of failure, in terms of reliability indices, or we can use characteristic values and partial factors. Now let's see what the differences are between assessment and design. The fundamental difference is the state of information. If we design a new structure, we start actually with a blank sheet, and we have to assume the properties of the future structure. To do so, we have our codes, where the variables are defined. And if we apply correctly the codes and the structure is properly executed, then according to the design, then the reliability will be more or less objective. It will be the reliability associated with the code rules. In existing structures, the situation is completely different. Very often we have only vague information available or even no information, but the structure is there, so we can measure its properties. We can also measure actions, etc. So that the reliability will depend on the available data. Sometimes it will also depend on the knowledge of the expert doing the assessment. So the reliability of an existing structure is more subjective than the reliability of a new structure. Since the structure is there, we usually apply a staged evaluation procedure. We have our construction in a natural and human environment exposed to certain hazard scenarios. In order to analyze the reliability of the structure, we in a first stage would assume very conservative assumptions for the different variables. If with these conservative assumptions we are able to verify structural safety, serviceability, and also fatigue in case of bridges, for example, then we are fine and we can use the structure also in the future. Otherwise, we would improve the information and verify against safety, serviceability, etc. We can repeat this procedure as often as we want, but normally we would stop if there are no longer doubts about the reliability of the structure, or if there is no margin for improvement. Then we would take a decision either to continue using the structure or maybe strengthen or even substitute the structure. There are different complementary approaches to updating. We can update the failure probabilities if we know some load effects, for example, if we carry out load tests, or if we have some information of loads applied over the past service life. Then we can update the failure probabilities. But normally we would probably update the basic variables where we use prior distribution function reflecting all information available before data acquisition is carried out. Here, this blue curve, for example, for an elastic limit of a steel. Then we have new observations for example, the results of a certain number of tests, which we then have to combine with the prior information, obtaining a posterior distribution function by applying Bayesian methods or other statistical methods. The representation of the results will depend on the verification method used. If we use probabilistic methods, then we would use the distribution function. If we use partial factor methods, for example, then we would use the updated characteristic value, in this case, of the elastic limit of our steel. Another difference between existing and new structures is deterioration. Of course, any structure is exposed simultaneously to mechanical actions and environmental influences. In design of new structures, we often separate the requirements and checks for the ultimate unserviceability limit states, where we consider normally the mechanical actions on the one hand side, and durability on the other hand side, where we use condition or proxy limit state verifications. This is not appropriate for existing structures, because in existing structures the deterioration may already be ongoing, so that the resistance may decrease over time, and we have to take into account the combined effects of deterioration and actions when we carry out our verifications. This is also the case because inspection and maintenance planning is not possible based on non-measurable indicators or proxy limit state verifications. In case of ongoing deterioration, the assessment should be based on shorter reference periods. The previous speaker was talking about this topic as well, whether the verification should be carried out for a lifetime or shorter reference periods. In existing structures, the reference period should be shorter, for example 1 year, and decisive would be the last year of the future service period. Also, the reliability requirements may be different in existing and new structures. In general, reliability requirements depend on the cause and mode of reaching a limit state, the direct and indirect consequences of failure in case this should happen, the relative cost of safety measures to increase reliability. It is much cheaper in new structures to add, for example, an additional rebar than in existing structures, and of course, as mentioned before, the reference period, so that lower levels can be justified for existing structures because the cost of safety measures are higher in existing structures. Replacement of existing structures may imply interruption of activities or even resettlement of population, and reduction of resource consumption compared to replacement. Also, verifications may be different in design or assessment. If a structure exists, we can assess this system based on past performance. We can do that qualitatively, where no reliability background exists, so this is rather dangerous, and it is not allowed in all countries, but in some countries it is done. But we can also do a quantitative assessment based on past performance, where we take into account previous information about, as I mentioned before, load tests or load effect histories, for example, and we can calculate conditional probabilities of failure, which we compare to some admissible value for these probabilities. But the normal case would be to calculate, to carry out the verifications based on updated variables, where we can use risk-based methods. We use updated variables to determine updated probabilities of failure, and if additionally we take into account the consequences of possible failures, we obtain the expected risk, which we can compare to some acceptable level of risk. Or we can also use reliability methods, where we do not directly take into account the possible consequences. And the normal case would probably be to apply partial factor methods, as we do also in design. And partial factors for assessment may be fixed, or they may be adjusted depending on the scatter of the corresponding variables and also on their relative importance in the limit state function. Finally, also the results may be different. If we do a design, we start with our sketches, then we do our calculations, we do our drawings, and finally our bridges are built, etc. So we have a clear definition of the load-bearing system, of the different members, the details, and the materials. In an assessment, the outcomes may be completely different. For example, the reliability may be sufficient for the remaining service life, then we are fine. Or it may be sufficient at the time when we perform our assessment, but not for the full remaining service life. Or it may even be insufficient at the time of the assessment, or our structure may be in such a bad state that immediate intervention is necessary. And also for the intervention, we have many different options. We may have construction interventions, operation interventions, etc. So how is all this treated in the Eurocodes? As we have seen, the general principles of structural reliability established in Eurocode 0, EN 1990, are the same for design and assessment. But as we have seen, there are important differences. Due to these differences, if we apply design-oriented rules to the assessment, then the outcome would be conservative. And this might lead to economic, ecological, or also socio-political consequences. In order to overcome these problems, there are different approaches. These approaches depend very much on national choices, but also on material-dependent preferences. Steel people and concrete people do not think in the same way, it seems, etc. So that harmonization certainly is needed. This has been recognized by the European Commission for Standardization, CEN, already 10 years ago. So a working group was started in, I think, 2012 to produce, first of all, a science and policy report, which has been published in 2015 by the Joint Research Center. It contains the policy framework, and a summary of existing regulations in different countries and different standards, etc., and also a prospect for possible future CEN guidance on this topic. Based on this report, a working group and a project team then established a draft for a technical specification, which was published in 2020. It complements Eurocode 0 for design, with general rules and also rules about actions for assessment of existing structures. In summary, all the differences that we have identified before are dealt with in this document on the staged assessment procedure when we are talking about assessment of existing structure, on the updating of information, on deterioration, different options for verifications, and different options for interventions. Of course, only from the point of view of the treatment of reliability problems. Then, after that, these technical specifications should be transformed into a future Eurocode. For this, another working group and another project team drafted recommendation or a part of the future Eurocode to convert the technical specification into a Eurocode for general rules for assessment and actions, and also a report on requirements and guidance on development of material-specific provisions was produced by this project team. It was also decided that this draft Eurocode should be the part 2 of Eurocode 0. Although this is not the final decision, maybe this will be changed in the future. However, the final documents are available since November of last year. The scope of the document, as I said, is the additional provisions to Eurocode 0 Part 1 for the design, but now for the assessment and retrofitting of existing structures. It contains also provisions for using updated data for basic variables, structural models, and failure probabilities, and rules for the assessment of structures in case of retrofitting. Here we have the list of contents, but to recover a little bit of time, I will skip this one. Also, the Eurocode, the new Eurocode 2 for concrete structures, contains an annex on the assessment of existing structures with additional rules for aspects not covered in the design part on previous old materials, on detailing, which was different, of course, in former times. Anchorage of plain bars is also a hot topic there. And it also contains generic considerations for deteriorations. In case of deterioration, according to this code, assessment should consider, of course, all relevant influences like reduced concrete sections, reduced area and ductility of reinforcement, stress concentration due to corrosion and stress corrosion, reduced concrete steel bond, loss of mechanical properties of concrete, cracking or expansion of concrete, etc. But there are no prediction rules for deterioration rates. And finally, I have no slide for that, also the Eurocode 8 for seismic design contains a specific part for assessment of existing structures, seismic assessment of existing structures, but this is not new because this part already existed in the first generation of the Eurocodes, although it is now completely revised. Let's now see some needs for further development. Sorry, I have to drink a little bit because I have a flu, it's not COVID. First of all, the reliability requirements. We have seen before that the requirements can be different for assessment of existing structures from those used for new structures. And we have also seen that the reference period preferably should be 1 year and not the lifetime. In the Eurocode 0, the part 1, actually we have indicative values for these requirements for 1 year, depending on the consequence class, and for 50-year reference period. And they should be, in fact, equivalent. They should lead to the same solution if we apply the corresponding requirements properly. But if we look closer at these values, which are indicated in terms of reliability indices, not probabilities of failure, although this is equivalent, then we see that actually these equivalencies correspond to a ratio of the probability of failure for 50 years divided by the probability of failure of 1 year of 50. This means that no correlation is taken into account, but in fact correlation exists because in subsequent years, for example, the self-weight will be the same, and also if we have no deterioration, the resistance of our structure will be the same. So there is some correlation. And if we take this into account, as we did here in this study, which I will not explain, then we would find that equivalent values for the typical 3.8 reliability index for 50 years and the consequence class 2, which we have here, would be, in the case of imposed load, 4.2, and in the case of climatic actions of the order of 4.5 and not 4.7 as indicated in the Eurocode. So this difference, of course, we can take into account. But we should go further, and requirements should be derived based on explicit risk analysis, considering, of course, human safety, but also economic aspects, including, I would say, consequences of unsustainable development. If we look at this figure here, where for different countries, the CO2 emissions per capita are represented versus the life expectancy, then we see that somewhere we must have an optimum. And some countries maybe here they call it overdeveloped. They may be overdeveloped. We could also call it maldeveloped. I don't know. But certainly we should think about that when we decide about reliability requirements. And finally, we also may take into account heritage values. Furthermore, indicative values should also be established for serviceability limit states, not only for ultimate limit states. Structural resistance, there are also many things to do. Just as a reminder, we have seen that existing structures may be affected by ongoing deterioration, leading to a decrease in the resistance, so that design resistance models may be inappropriate for assessment. We cannot directly use them sometimes. There may also be other reasons why we cannot use design resistance models directly for assessment, so that we need assessment-specific provisions in the material-oriented Eurocodes. Such models should explicitly account for the effects of deterioration on the resistance. They should be generally applicable for design and assessment. That would be the ideal case, but we may also adjust design models for assessment, or we can elaborate, of course, new models for assessment where we could take into account the effects of deterioration. And finally, we also will need models, of course, that describe the propagation of deterioration in order to make previsions of the performance of our structures at the end of the future service life. What is important is that these models should be based on mechanical principles. It should not be statistical models. This is important. So that, for example, for corrosion, you're all experts, the main effects of reinforcement corrosion should be taken into account. That is the decrease of bar cross-section, the stress concentration due to uneven corrosion, as we can see here, the decrease of ductility of steel, if relevant, strains due to the expansion of corrosion products, influencing the translation of material strength, which we establish using these normal standardized specimens. But what we actually need is the resistance of the concrete within the structure, and this we must take into account, and also, of course, the cracking and the loss of concrete cover. All these kinds of mechanisms should be introduced in mechanical models to establish the resistance of deteriorating structures. Then we come to the uncertainties. We have seen that the reliability requirements are linked to the uncertainties associated with the standardized rules, so that the assessment should be based on actual conditions, the actual conditions of the structure we are analyzing. To this, we update information, as we have seen. This leads to a change in the uncertainties associated with the variables, so that we need probabilistic models associated with the code rules, which can be used as the starting point when we do updating. So we need to know what is behind our code rules for all the variables. We have some information on that because currently there is a report being produced with the background of the reliability aspects in the Eurocodes. It should be published also as a JRC report very soon. But many parameters also depend on national circumstances, of course, if we think about climatic actions, etc. So there is a lot to do, at least in some countries. In others, this has already been done, and we have probabilistic information associated with the action variables. Similarly, on the resistance side, also in this future background report, we have information, but further information is needed and should be given in the material-oriented Eurocodes. And also here, we have many national parameters, because in the past, in many countries, the construction procedures and preferences were different, of course. So there is still a lot to do in this field. If we look at resistance models as an example, resistance models or the resistance of a structure depends normally on some material parameter, on some geometric parameters, and also on the precision and the completeness of the models. Model uncertainties are considered in this context as random variables. Now, if we think about existing structures, updating of material strength and geometry is more or less straightforward. Of course, it is not always easy, but it can be done. But what is difficult actually in practice is the updating of model uncertainties. But if we do updating, for example, of material parameters, we need to know what is behind the partial factor we use for the design. Otherwise, when we do the updating, we may come to equivocal conclusions. So we need to know the parameters behind the partial factor accounting for the model uncertainties. Now, normally, model uncertainties are inferred based on a comparison of experimental results, like here, and some theoretical values. Of course, for theoretical models, we can use very simple models, we can use nonlinear finite elements, we can use many things, yeah? And there are many influences affecting both types of results, the experimental results on the one hand side and the theoretical results on the other hand side. What we then do normally is compare both, and if the results do not match, we normally adjust our theoretical models. But maybe sometimes we should also adjust our experiments because, of course, there may also be some errors or some uncertainties in it. So based on this kind of comparisons, we usually deduce or infer our model uncertainties. However, in reality, things are a little bit more complicated. Test specimens are normally of limited size, what we can do in a lab, and the outcome of such tests or of the corresponding models we then use to design this kind of structures. Yeah? And of course, there may be some kind of size effects. Also, the quality assurance or boundary conditions, loading conditions, thermal and moisture effects may be completely different in the lab and in reality. So what we actually would need is a comparison of the structural performance of real structures and what we obtain from our experimental and theoretical models. But of course, this kind of information usually is not available if we are talking about failure, of course. Yeah? So that if we have something, normally it comes from a comparison of theoretical and experimental results. But what we would need is this here. Yeah? So that the model uncertainties for resistance depend, of course, on the type of structure and on the failure mechanism. This is the reason why the material-oriented Eurocode should contain the numerical values of the partial factors covering the model uncertainties. This is normally hidden somewhere and we do not know it. They should also define the uncertainties covered by these values, these numerical values, and they should define the statistical properties of the variables describing these uncertainties. And all this information should be provided for the models for the design of new structures, if they exist for adjusted models to enable assessment, or if we have new models or will have new models to enable assessment. They should also be described, the corresponding uncertainties, and in the same way, the uncertainties should also be described for the models for structural resistance after strengthening or rehabilitation, etc. Also here, there is a lot to do still. Also in the field of robustness, there is certainly a need of further information or further research. Redistributions due to local failure may lead to successive collapse of other components as a domino effect, we can say. This is a picture from a recent failure in Miami 1 year ago, I think. So that unsafe designs are possible even if code requirements are fulfilled for individual members, for all individual members. This is the reason why most codes include some robustness requirements, in the sense that they say the consequence of damage should not be disproportionate to the original cause. Now, such generic robustness requirements are mostly not further developed. There are no operational rules, or not sufficient operational rules. And this is related to the absence, in my view, of a practical metric for robustness quantification. Robustness is difficult to quantify. And of course, it is related to the complexity of the problem at hand. In this context, the conceptual design is most important. The choice, when we are talking about conceptual design, we are talking about the choice of the type, layout, and main dimensions of a system, of the individual members, of the details, and also the selection of the construction materials. Then, the conceptual design should also include the identification of members influencing the system reliability or stability. Not all members are equally important. And it should include the choice of a resistance mechanism after failure of those members. They are called key members. Now, this can be done, of course, for new structures, sorry. But we should be aware that any conceptual solution for increased robustness may worsen the performance for other hazard scenarios, and that is the difficulty associated with robustness. If we now switch to existing structures, of course, conceptual changes are very difficult or even impossible in existing structures, at least if we do not want to proceed to any constructional intervention. Therefore, what is most important is the unequivocal identification of all relevant hazard scenarios and hazard scenario, particularly in existing structures. But we also would need operational rules beyond general strategies for providing or verifying structural robustness. For this, we need, of course, some quantitative criteria for decision making. What we have proposed for the draft of the future model code, the 2020 model code of FIB, is the introduction of different reliability requirements for normal situations and normal members. We have the normal code requirements for the reliability. For key members, where the key members are those members which are decisive for the system strength and stability, we would use, and identified situations, we would use the maximum value out of this normal code value, the 3.8 value for consequence class 2 and 50 years reference period, as we have seen before, and on the other hand, a requirement for human safety. And then for the remaining system, after possible key member failure, we would need a conditional reliability requirement for this system, because we want to avoid the collapse of the remaining system, at least as long as we need to, for example, evacuate the whole building or whatever structure we are analyzing. We have inferred such reliability requirements for human safety. I will not bother you with details about how we did that. But what we have obtained is different reliability requirements. Here on the vertical axis, we have the reliability requirement, the reliability index for a 1-year reference period, depending on the collapse area and depending on the consequence class. Consequence class 1, 2, and 3, depending as defined, for example, in the Eurocodes. And we distinguish between design and assessment. As we have seen before, there are reasons to allow for lower reliability requirements in existing structures. The difference is roughly 0.5 in terms of the reliability index. Let's see now how we can apply this. For this example, it is an extra-dose bridge. In such a bridge, of course, the key members would be the ties, certainly, and also the pylons. What are possible robustness strategies? In the case of tie failure, we would introduce an alternative load path where loads can be transferred to the foundations by means of some membrane action of the deck, in this case here. And in case of pylon failure, there of course is not much possibility to introduce some alternative load path if something like this happens. But what we want to avoid is that if this collapsing part here drags down the remaining part here. Yeah? And to do this, what we can introduce here is some kind of built-in fuse. Of course, we have to make sure that in case of pylon failure, the fuse really works. Yeah? And this we can verify also by calculations. Now, although this fuse works, if we do it properly, we do not want the pylon to fail for identified, persistent and accidental design situations, of course. We do not want to take this risk. And for this pylon, therefore, we use for the identified situations the maximum value of the code reliability requirement, and this reliability requirement based on human safety. And in this case, for the collapse area, we have, in this case, and assuming a consequence class 2 for this bridge, indeed, this value is larger than the code value, so that we design for the identified situations the pylon for this reliability requirement. Another field where we can improve things is monitoring. As it is well known, different causes may lead to non-compliance of any particular requirement. There may be deviations from the expected actions, for example, and there may be deviations from the expected resistance for many reasons, so that we can quantify parameters related to such influences, and this quantification may provide evidence about the degree of compliance with the corresponding requirement. This is the reason why we are talking about indicators, reliability indicators, in analogy what is done in other fields like economy, medicine, etc. Now, what is the best choice of the parameters to be quantified? The best choice will depend on the sensitivity of structural reliability to their variation. If there is no variation of the reliability, there is not much sense to measure the corresponding parameter. And this we should take into account when we define a monitoring program for an existing structure. If we do that, for example, in this case, we can decide to measure the strains, for example, here in the hogging bending area where the bottom flange is under compression. Now, measure things is okay, but it is not sufficient. So we also have to establish threshold values, and this we can do by structural analysis, as we do also when we design a structure. By structural analysis, we can determine the admissible or these threshold values and also the admissible average outcrossing frequencies. If we have that, for example, as I said, for this bottom flange here, the more it is compressed, the worse is the situation. For example, here we have the threshold which can be outcrossed, let's say 50% of the time. Then we have a threshold which can be outcrossed once a week also here when we are talking about safety, or once per year. These threshold values can then be compared with the measured values, and if there is too frequent outcrossing, of course, an alarm would be activated and we can adopt the corresponding measures. So that monitoring is a very rational tool for risk control. It contributes to the optimization of operation costs for structures, new or existing. But guidelines are certainly needed for the choice of monitoring strategies and also for the analysis of data. So I come to the end. I hope that I respected the available time. In the assessment of existing structures, many uncertainties may be reduced. A proper assessment based on incomplete or defective information may be completely wrong. So that the correct updating of information is certainly the most important step in a structural assessment. And careful planning, execution, and evaluation of tests is really the most important thing. Probabilistic methods are most accurate to take into account site-specific data, but such methods are not fit for use in normal daily practice. They are normally only used in very special cases. Therefore, rational decision-making should be possible, and it is possible by using partial factor format for assessment, but there is a need for research, in particularly also in relation with the assessment of deteriorated structures. So thank you very much for your attention.